Latches are the basic storage elements that operate with signal levels, rather than signal transitions. They are level-sensitive devices that are useful for the design of asynchronous sequential circuits. They generally have two inputs and one output pin. Latches are used to construct flip-flops, which we'll get to later on in this module. They can also be used with more complex clocking methods to implement sequential circuits directly. Latching is where the output of the circuit depends on the previous state and the present input value supplied, with the output value being constant. Let's take a look at the most basic, the SR latch. The set reset or SR latch is a circuit constructed with two cross-coupled NOR gates. Latch has two inputs, labeled S for set and R for reset, and two outputs, Q and Q naught. The upper NOR gate has two inputs, R and Q naught. The upper NOR gate produces the next state, Q. Similarly, the NOR gate, the lower one, has two inputs, S and Q. It produces a complement of the next state, Q naught. Under normal conditions, both inputs of the latch remain at 0 unless the state needs to be changed. The application of 1 to S causes the latch to go to the set state. The S input must go back to 0 before R is changed to 1 in order to avoid the occurrence of an undefined state. As we can see from this table, the SR latch performs three types of functions: hold, set, and reset based on the input conditions. In this animation, we can see a quick demo of the SR latch. We start with set equal to 1 and reset equal to 0. Q is stored as 1, and when we go back to 0, 0, it remains that way. Next, we change the reset to 1. This changes Q to 0 and Q naught to 1. When we go back to 0, 0 for the inputs, everything remains the same. Finally, we try 1, 1 as an input. This gives 0, 0 as an output, but it violates the constraint that the outputs are complements of one another. We can also see the changes in state for Q and Q naught for different configurations of S and R in the timing diagram from the textbook, although this static version is a little more difficult to decipher than the animated version. We can also make a latch with NAND rather than NOR. This is a version I learned a long time ago. In comparing the NAND latch with the NOR latch, the input signals for the NAND require the complement of those values used for NOR. Because the NAND latch requires a 0 signal to change its state, it is referred to as an S0 R0 latch. The operation of NOR and NAND latches can be modified by providing additional control input that determines whether the stated latch can be changed. In this diagram it's C, although sometimes it's labeled as EN for enable. You'll notice that this one has a few more NAND gates. When C or the enable is equal to 0, there can not be any change to the latch. When C is equal to 1 and the other inputs are both 0, again there are no changes. When C is 1, S is 0, and R is 1, we are in the reset state. When C is equal to 1, S is equal to 1, and R is equal to 0, we're in the set state. Like the NOR version, we need to be careful when all inputs are 1. The SR latch with control inputs is an important circuit because other latches and flip-flops are constructed from it. There is one drawback to the SR latch. That is, the next state value can't be predicted when both inputs S and R are 1. You can overcome this difficulty by the D latch. It's also called the data latch. The circuit has an input D along with an enable. The two outputs are Q and Q naught. The complement of the D input goes directly to the S naught input, and D is applied to the R naught input. As long as the control input is 0, the latch has both inputs at the 1 level, and the circuit cannot change state regardless of the value of D. When C is equal to 1, we sample the D input. If D is 1, the Q output goes to 1, placing the circuit in the set state. If D is 0, output Q goes to 0, placing the circuit in the reset state. As previously mentioned, the D latch receives its name from its ability to hold data in its internal storage. The binary information present at the data input of the D latch is transferred to the Q output when the control input is enabled. The output follows changes in data input, as long as the control input is enabled. When the control input is disabled, the binary information that was present at the data input at the time of the transition when C occurred is retained in the Q output until control input C is enabled again. Another latch is the JK latch. It's similar to the SR latch. This latch consists of two inputs, J and K. The JK latch eliminates the ambiguous state from the SR latch. When the inputs of JK latch are high, the output toggles. The output feedback to its inputs is the only difference that can be seen here, which is not present in the RS latch. Besides the SR and D latch, there are some other less common latches, such as the T latch. Thanks so much as always for watching. Next time we'll talk about flip-flops, and no, I'm not mispronouncing slippers here.